everyone. Today we are going to see an interesting topic. It is coordination number and packing factor and BCC structure. Is first we are going to recall some important points. So X-ray diffraction pattern, how these patterns are formed, that already I explained, and the important thing or important form is DHKL is equal to A by root of H square plus K square plus L square. Here A is the lattice constant. Already I told what is lattice. It is an array of points. Here the points represent atoms, and here H, K, L are the Miller indices of the planes. So what are the topics now we are going to discuss? So introduction to coordination number and atomic radius, determination of atomic packing factor of simple cubic structure, and BCC cubic structure, that is body center cubic structure, and use of atomic factor in real world applications. So that and all we are going to see now. So to measure a packing efficiency, how can we measure a packing efficiency? So determines how tightly atoms are packed with the crystal structures. So based on that we can measure the packing efficiency. That means the distance between the two atoms should be less. So next is to relate the structure with the density. So it helps to calculate the material density and compare how different crystal types occupy in the crystal space or atomic space, and to predict mechanical properties. It explains why closely packed structures are more ductile than loosely packed ones. Here the closely packed structures are FCC and HCP, and loosely packed structures are BCC, that means body center cubic systems. And to analyze the material behavior, useful in understanding diffusions, corrosion resistance, and void space in material. Let's explore the characteristics of unit cells. So the number of what are the parameters we are going to discuss? First one is number of atoms per unit cell. Next is coordination number, then atomic radius, and atomic packing factor or a packing density. So what is the number of atoms per unit cell? Each and every unit cell contains based on its structure, it contains some number of atoms, and each corner one atom is placed. And coordination number, it is number of equidistant nearest neighboring atoms to be a particular atom. And atomic radius, it is half of the distance between the nearest neighboring atoms. And atomic packing factor or packing density or APF, it is the ratio of volume occupied by the atoms in unit cell to the volume of the unit cell. So these four parameters are very important, and these parameters gives about the complete detail of a unit cell. So now we will explore. The first structure is normal cubic structure, and this structure is called simple cubic structure. And the second one is how that unit cells are combinedly form an entire structure of the crystal. And here A is called lattice. Here number of atoms present in the unit cell is 1, because all the corners are shared with it contains all the corners, means the cubic structure, it contains 8 corners. So each and every corner can share with 4 more unit cells. So it forms a complete structure of the crystal. Their coordination number is 6, and atomic packing factor is 50.52. Next is body center cubic structure. So body center cubic structure, all the corners contain one atom, and at the center it contains one atom. And all this pictures gives the idea about how the atoms are packed in a crystal. So here number of atoms per unit cell in body center cubic is 2, and their atomic radius, that means distance between the body center atom and any one corner atom, so that distance is root 3 A by 4, and its coordination number is 8, and its atomic packing value is 60.68. So what are the applications of packing factor? This factor used in semiconductor industries, material science and X-ray diffraction. How it is used in semiconductor? Essential for epitaxial growth of thin films. So silicon wafers are often cut along 100 planes. Already I told you what is 100, three coordinate systems x, y and z. Here x is present and y and z axis it is not present, so that represent 100 plane for device fabrication. And materials, in material science they are vital for understanding crystal growth. This impacts material properties greatly. And for X-ray diffraction, it plays a very important role in research. Miller indices help predict diffraction patterns. So what is a pattern that can identify using Miller indices? This is crucial for material identification. So this is the packing factor calculation for simple cubic and body center cubic. So APF, it is atomic packing factor, it is equal to 1.4 pi r cube by 2 r whole cube. And the APF for BCC is 1 plus 1 whole cube by 4 pi 4 r whole cube. So curiosity challenge, that means a question time. So calculate the APF for each crystal structure. So easily we can find simple cubic, BCC and FCC, and compare the efficiency of all for all the three packing atoms in that structure, and explain the structure you choose for and maximum strength to weight the ratio. So better ductility and corrosion resistance we can find using the result of atomic packing factor. It's a quiz time. So define atomic packing factor in your own words, then derive the formula for APF of a simple cubic structure. Explain why a BCC structure has lower packing efficiency than FCC, and calculate void fraction for a simple cubic structure, and write any two applications where high atomic packing is advantageous. Yeah, these are the references.